Hello everybody and welcome back to another Bentley Davey Tutors video. So today we've got something a little bit different. Today I will be doing a science video on the topic of chemistry at sort of a Year 9 curriculum level. So yesterday you may have missed it, but Luke actually posted a video more so focusing on earth and environmental sciences. So he was speaking a lot about land management and things like that, and greenhouse gases and all that sort of stuff. But I wouldn't be surprised if you'd missed it because it was very boring. I watched it myself. The monotonous voice really didn't help. So if you're wondering why I've come out attacking him here, if you hadn't seen the video, he decided that it would be a good idea to put in a Jeremy roast counter, despite missing one of the five in the video. He couldn't even count, it was 5. But because I'm not that childish, I won't stoop that low, and instead I'll do what you're actually here for, which is learning the content. So basically what I'm looking at today is chemistry at a bit of a Year 9 level. So for our curriculum at least, we've got a set of 15 sort of learning outcomes. These are the things that you need to know for this unit. And so what I'm going to do is I've written some notes on each of those, and I'm just going to go through them and explain different sort of areas of the topic of Year 9 chemistry. So a lot of this might be fresh knowledge, or hopefully it's just a refresher. But if it is fresh knowledge and you want to take it down, you can feel free to follow along, take some notes, or you can just sit back and try and take in anything that I say that might be remotely interesting or important to know. So basically what this video is going to discuss is all sorts of things about chemistry. I speak about atoms and the makeup of atoms, including the electrons and everything like that. I speak about reactions like endothermic and exothermic reactions. I look at products versus reactants, and then finally we cap it off with some physics laws that are just thrown in there at the end. So to begin with, I'm going to speak about the atom and the location and features of protons, neutrons, and electrons. So how an atom basically works, at its most basic, is what you've got the nucleus, which is made up of protons and neutrons, and then you've got electron shells around the outside of that. And so the protons and the neutrons, so the number of protons in a nucleus makes up an atom or an element's atomic number. So if you've seen a periodic table, all of the different elements have a big number there, and that's their atomic number. And we'll get, there's also a couple of other numbers on there which we will discuss more a bit later in the video, but they all explain different things. And so atoms and nuclei can have different numbers of neutrons in the nucleus, but this creates different forms of the same element that actually have different levels of radioactivity, which is quite interesting. So say you could have a helium atom, which will have 2 protons in it, and then some amount of neutrons in it, and so it could have 2, but it could have less, or it could have more, which are called isotopes. Yes, they are called isotopes. I definitely didn't just have to check that because I wasn't actually sure of what I was saying, but that's right. So we've got different numbers of neutrons which make different isotopes, which can have different levels of radioactivity. Then we have the electrons, which will float around the outside. The old idea was that they were in perfectly round shells, but it's now more accepted that they sort of just float around the place, and they have a negative charge. So protons have a positive charge. Neutrons, you would think, have a negative charge because it starts with N, but no, they actually have a neutral charge because, to be fair, it is closer to the word neutral than it is to negative. And then electrons have that negative charge. So all atoms and all elements should theoretically have a balanced number of protons and electrons, which would give it a balanced charge, but then there can also be ions which have different numbers to make it either negative or positively charged. So that's sort of all we've got in terms of the actual makeup of the atom there, but then we will now move on to the second outcome which we've got, which is distinguishing between atoms, molecules, and compounds. And this is always something that has confused me a bit because everything can sort of seem quite similar when you're talking about these 3 ideas. But yeah, we've got 3 things here. So firstly, you've got an atom. This is any single atom or element. It's just one thing. That's pretty basic. Then you have a molecule. So a molecule is any 2 or more of the same element or the same atom that are together, basically. So if you had two Yeah, so if you had two hydrogen atoms together, that would be a hydrogen molecule. And then finally, you've got a compound, which is pretty much a physical combination of two or more of any different elements or atoms and any number of them. So that's sort of the differences between atoms, molecules, and compounds. And then the next thing that I wanted to look at here in the outcomes, and I touched on it a bit before, is distinguishing between atomic mass and number. So, atomic mass, actually, I'll start with atomic number, because that'll be easy for everyone to follow. So, atomic number is that number that I was talking about before. That's the big one that you see in the middle of the element. That is purely the number of protons in that element. So, for example, if I had carbon, which has an atomic number of 5, no it doesn't, it has an atomic number of 6. And so that purely means that it has 6 protons in its nucleus. And then we've got the atomic mass, which is slightly different. It's also a number that's on there. But yeah, it differs because the atomic mass is actually protons plus neutrons plus electrons. So how it works is protons and neutrons basically have an atomic mass of 1. That's how they work. They're just 1. And then electrons have a tiny, tiny, tiny mass, which I think is 1 in 1,814 or 16 or somewhere around that. But they're very small. So how you get an atomic mass is you add up the protons, the neutrons, and the electrons. Now, in a normal non-isotope version of an element, your atomic mass should be just over double the number of protons. So just over double the atomic number, because you'll have an equal number of protons and neutrons. So say with our carbon number example again, you've got 6 and then 6 neutrons. So that is 12. And then you've got the same number of electrons as you do protons, but those are really, really small. So you go just a bit over that number, and that's where you get your atomic mass. But it's important to be able to distinguish between those two. And so the next thing that I'm going to look at here is describing the way that electrons are arranged around a nucleus. So I discussed this a little bit before, and I just touched on it, how the old version was that they're in perfectly round shells, but it's more commonly accepted now that they just sort of float around like they've got nothing to do, and they're just sort of chilling there. But in terms of the shells, which is often what you need to analyze and look at if they wanted you to draw something called a Bohr diagram, which is where you've got a nucleus in the middle and then shells, which are just circles around the outside. And so they are arranged in a specific way in these shells, which can be calculated with the formula of 2 to the n squared. No, it's not that. 2 times n squared. Or just 2n squared. With n being the number of that shell. For example, shell number 1 is 2 times 1 squared, or 2. The second shell would be 2 times 2 squared, which is 8. The third shell would be 2 times 3 squared, which is then 18. So that continues on going. However, it is more commonly accepted, especially at younger years, that the shells go 2, then 8, then 8, because you probably wouldn't have to go much further than that anyway. So then up next, something that's important to look at in terms of a periodic table is the relationships between some different types of elements in terms of groups and periods. So there are 2 different things that we've got on a periodic table. You've got your periods and you've got your groups. Periods go down the table, and there are 7 of them, and groups go across, and there's 18. So what are groups firstly? Well, how groups work is that every element in a group which goes down has the same number of electrons in the outer shell. So, for example, you've got your alkali metals, which could be something like francium or lithium, and they would both have 1 electron in the outer shell because they are in group 1. And then you'd have something in group 6 where all of them would have 6 electrons in the outer shell. But then periods are slightly different. They're the ones that go down the page, and they're in columns, and they sort of relate more so to sometimes the radioactivity of certain elements, and also sort of what they're like. But there's not as much of a sort of interconnected relationship there. Or one thing that I could say is that all the period 7 elements are radioactive, which is something quite interesting about them. And then so onto the next bit I had here, which was just to identify some features of some specific families of elements which are like the groups. So what I thought I'd look at was 3 families or 3 groups, which are the halogens, the alkali metals, and the noble gases. So firstly, with the halogens, they all produce salts, when added to sodium. For example, NaCl, which is sodium chloride, or actually just table salt. But yeah, all of them produce salts when they are combined with sodium. The alkali metals, these are highly reactive, especially in water and specific conditions. And then they are shiny, soft, and silvery. And this could be something like sodium. Sodium is an example of an alkali metal. Finally, we've got the noble gases. So these are very low reactivity, and this could be something like helium or neon. So they are normally quite safe, which is where the name noble gases comes from. So the next thing that I wanted to sort of look at here, the next section of this video, we'll be speaking more so about radiation and how that sort of goes about in the world. And so I'm going to look at the use of nuclear energy and the radiation with that in both medical and industrial fields, and the pros and cons of each. So firstly, in terms of medical, some pros is it's really great at treating certain diseases such as cancers. And this is because it's highly targeted and efficient at doing things such as killing dangerous cells. However, there are some negatives associated with this in terms of using nuclear energy in the medical sense, which would be a high amount of dangers that are associated with it, such as many long-term effects on your cells due to the high levels of radioactivity that come from it and radiation that come from it. And in terms of in an industrial sense, this could be something like powering homes with nuclear power. Some of the pros are that it's highly efficient in terms of the amount of energy it produces, and also the world has a lot of uranium, and the process of creating nuclear energy using uranium is it's very efficient, so it doesn't use very much uranium for what you're getting out. But the negatives here is that there's a lot of stigma around the consequences of nuclear power plants, specifically, as well as the consequences that can come from meltdowns, such as from natural disasters, which is why they're not as highly utilized around the world. And then so also I'm going to have a look here about different types of radiation. So there are three main different types of radiation. This is alpha radiation, beta radiation, and gamma radiation. So firstly, alpha radiation. So these three, alpha and beta radiation all occur when nuclei decide to start decaying. And so what alpha radiation does is it shoots out something exactly equal to one helium atom from the nuclei. It's not actually a bit of helium, but it is two neutrons and two protons, which are shot out from the nuclei. And what this does is it means that it decreases the atomic number of that element by 2 and the atomic weight by 4, because it's taking out something that's worth 4 in weight and 2 in number. But this radiation can be quite easily stopped by something even like just a piece of paper, or especially a thin bit of metal. So up next we got beta radiation. So this shoots out exactly one electron, and how it does this is it changes one neutron into an electron and then shoots it out. Because if it just shot out one electron, this would make it then an ion of the original element. And so instead what it does is it takes out one neutron, which just changes the isotope of that element, and then it shoots that one out. And this one is a bit harder to stop, so you need something a bit more like a thick piece of aluminium in order to stop this radiation from continuing on. And then finally we've got gamma radiation, who has decided that it wants to be a bit special. It's going to be a bit different to the other ones. So this is a wave, whereas the other two were particles. Gamma radiation is a wave, so it's like, ooh. Okay, that was really disappointing that I just did that. But anyway, it's a wave that goes up and down like that, like how a normal wave would. And so what it means is that it's got no weight or mass, and it also has no physical size or area or anything like that. And so it's not made up of anything really, because it's just a wave, so it's just energy, and it is a lot harder to stop. So it's going to get through paper, it's going to get through aluminium. You pretty much need like lead to stop this, so maybe some thick lead which would be able to stop it. But yeah, so that's sort of all we've got there on different types of radiation and what they do. But that takes us up to reactants versus products and other different things in terms of reactions. So on the topic of reactants versus products, so what we see is in a chemical reaction, reactants are on one side, products are on the other. So reactants are what you put in, they then react, and then products are what you get out on the other side. So for example, in the reaction of photosynthesis, we see that carbon dioxide plus water creates energy in the form of glucose and then oxygen as well on the other side. So we see that the reactants there were the carbon dioxide and the water, and the products were the glucose and the oxygen. So up next, we've got the topic of exothermic versus endothermic reactions, which are two different words to describe how a reaction basically occurs and what happens as a result of it. So exothermic reactions are ones which produce heat from the reaction, which means that the products that come out on the other side are usually like hot or warm. And so what happens here is that heat comes in here in terms of a reaction as a product. An example of an exothermic reaction would be something such as combustion, where you basically burn something, and as we all know, heat comes out of that. Whereas an endothermic reaction actually takes in heat for the reaction. And so the products here would be cold or maybe just room temperature. And so what that means is that heat comes out here and it's in the reaction as a reactant. So it's not on the other side. And an example of this would be photosynthesis, where heat is used as a bit of a catalyst or almost something that goes in as a reactant. So what this means is exothermic basically means hot or produces heat. Endothermic means cold or takes in heat and makes the reaction, basically makes it colder. So up next we have combustion versus respiration in terms of energy release. So I'll be speaking to you all here about reaction rate and energy release and how that sort of works. And so two examples of two different reactions that we can look at to have a look at energy release and the rate that occurs are combustion and respiration. So both the reaction rate of both of these heavily depends on the amount of oxygen you have, because we can see that combustion can either occur as complete combustion or incomplete combustion. This is completely based on the amount of oxygen that the reaction has to burn and to basically do what it needs to do. Complete combustion releases far more energy than incomplete combustion does, as it can properly complete the reaction in the way that it needs to and produce all the heat that it needs. Then we've got respiration, and the speed here of energy release is completely based on the amount of oxygen as well. During exercise, when you're taking in a lot of oxygen in what's called an anaerobic activity, this reaction rate will be much, much faster because you have a lot more oxygen going in, which can increase the rate of respiration. However, oxygen debt can also build up when you have too much oxygen, which then has to be dealt with by your liver in the form of lactic acid and removing that lactic acid. And then continuing on the idea of reaction rate, there are several factors which can actually increase reaction rate when you're taking part in a reaction. So pretty much everything that you do to a reaction can increase its rate, and this is mainly things such as the surface area of the thing that you're looking to react, the temperature, and then catalysts such as enzymes and magnesium normally increase the reaction rate. So for surface area, if you're putting something solid into either into a liquid or into some sort of acid, the amount of surface area of the thing that might be solid, or the amount of surface area that is coming into contact with the thing that is the liquid or is the acid, will increase how fast the reaction occurs. As well as this, we see that the temperature, often the higher the temperature, the higher the reaction rate goes, because heat can act as a bit of a catalyst for the reaction. And then finally, we have some actual catalysts such as enzymes that can be found in the liver, and also magnesium, which is quite a good catalyst in terms of speeding up a reaction. Now, the final thing I wanted to look at was the law of the conservation of mass and then the law of constant proportions. So firstly, on the law of conservation of mass. What this basically states is that mass is not created or destroyed. This is quite similar to the fact that energy is not created nor destroyed. But basically what it's saying is that everything on one side of the reaction will have its weight represented on the other side of the reaction. So let's just say, for example, if I put in some reactants that weighed 300 grams, whatever products I got out should also weigh 300 grams. Now, you could cite the fact that things such as gases escaping would have some weight, which is very true, but in terms of this law, you would cite that any sort of gas that was released as well would have to be included in the weight. And so then the last thing here was the law of constant proportions. So what this basically states is that all pure compounds will always have the same ratio of things in them. So what that always means is that water, pure water, will always have the same ratio of hydrogen to oxygen as any other size sample. So you get a one size sample of water, and it will always have the same ratio of hydrogen to oxygen if it's pure water as another sample. So that is all we have here today in terms of chemistry at a Year 9 level, for us at least, in terms of the areas that we're covering here on the channel. I hope you enjoyed the video. It was a bit of a rush to make this tonight, so I apologise if any of the information's wrong, which, let's be honest, it probably is. But most of it is backed up by some good research that I've done, so it should all be okay. But it's always important to, if you're studying this, do some of your own study, because you shouldn't always rely on what other people, especially us, tell you. But yeah, if you did enjoy, leave a like, subscribe. We're going to have loads more videos coming out in the next week or two. Especially, there should be another video on science coming out tomorrow. And then there will also be more Macbeth videos coming out throughout the rest of the week. And if you haven't checked out any of our past videos yet, make sure you go and do that. Because they're sometimes a bit of a laugh and they should be able to teach you something. So, hope you all enjoyed. Thank you and goodbye.